Okay, for the very last major topic, what we're interested in doing is looking at the binary search. Now, binary search has a couple of presuppositions. The first one is that it always has to deal with a sorted list. So whether you use the bubble sort first before you run this, or whether you have a check in your class to say the list is sorted, you need to have that. You also need to make sure, obviously, that you have a list that you can search in. So let's assume that with a binary search, because we're dealing with integers, you pass in the search criteria as an integer, and it's a value that you're going to pass in. So how would the binary search be coded? Well, obviously you need to do your if checks for if it's sorted and it's big enough, right? Otherwise you just return nothing. What you're going to do is if you find a list node, you're going to return a reference to it. Okay, that's if you find it. So let's draw this out as a simple picture. As we say, we're going to keep a concrete image in front of us, and it's sorted 4, 27, and say 30. Okay, so that's your sorted list, and your bubble sort or whatever mechanism you did to sort it, you sorted it. You know that it's sorted, so it's safe. You now have a very interesting, this looks very much like an array. And when you're searching through it, having access and treating these almost like index positions underneath is a very, very helpful way of coding it. But because a list doesn't typically have indexes, you have to either do one or two things. You have to go back to your list code. So what you can do with your list code, and this could make your code really complicated. That's a value, but for each list node, you might want to store an index. Now, personally, I think that's a very complex move to make, because as you move this list node around and you swap items, for example, one of the critical elements would be that you'd have to change its index in addition to going through the whole swap procedure. You may think that's adequate and that's fine. That's a possibility. The second mechanism is to generate indexes dynamically by doing some kind of count facility, because you know you've got access to the head, you know you've got access to the tail, so you could do a count method which could count how many items. And the reason that you know you're at the tail is the item immediately after the next item on there is null. So that would give you a good way of checking as you worked your way through it and looped through and did a count. So is the next item null? No, add one. No, go to the next, go to the next, go to every time you ask. And then you've got a simple count method, right? And that count method would return how many items you have in here. In this example, I've got 9. Deliberately, well, an accidental odd number, but it's worth thinking about. So I'd need some kind of count, but I'd also need to use that count to find the middle point. And the way, in order to function with the binary search, let's say I get a count, so I know how many items I have, okay, or a length. I write my own length method for my list. Right, so that's the first challenge. You need to have that as a separate challenge, gives you that back. So then I know, so if I've got 9, if the length returns 9, which it would do for here, I need to find the halfway point, but it's uneven. It's 4.5. So actually it's 2. Well, I could either take 4 or I could take 5. So what do? Well, in this case, it's really, really quite trivial whether you go one up or one down. I would simply just round it up and get the midpoint, which returns, say, a 4, right? So you have a method which calls midpoint, and the value you pass in is the length. You divide it by 2, and you also make sure that you just take the integer part, so you get the midpoint going 4 along. So it would go 0, 1, 2, 3, 4. So it would return 9. Okay, now let's say that I'm actually seeking, the search I'm doing is to find 27. Okay, that's the number I've put in. So let's just talk this thing through and how you would code it. So I get a mid thing which would give me that value. I now need a loop. And what the loop needs to do is it needs to say whether this value is greater than the midpoint. Because if it's greater, then actually I don't need to, I can ignore everything on this side and I can treat this little section as if it's a small list of its own. So then I would point my bottom there, my top item there, I'd count how many I have here, and then from that point divide that by 2 and give me one of the midpoints. And let's say that it just gave me that one. Okay, then again I would check the difference between that. That's greater, so then I discard all of that and then I do a comparison with that. So the binary search has some quite interesting conditions. It's not a ton of code, but what it does for you is it really does test your ability to create sub methods within your code, mid methods, a seeking method perhaps to find a particular location, which you do dynamically. You don't do them fixed in a fixed way. And the point of that is that you then don't need to go back to your list node and start adding in indexes, because that is going to complicate things and easily go out of synchronization. The list node mechanism of swaps and what you do with it should remain as straightforward as it is, and your binary search code should create dynamic methods to allow you to split it, do the difference calculation, then split this side, find the midpoint again. So there's a lot of counting methods inside here, a lot of dynamic indexes, as I would call them. They're not fixed indexes, they're dynamic. They're values you have to ask for and the code has to give you back. So a mid method would be a mid index method. You might want a bottom index and a top index as well. Okay,